Today we're going to take a step back from integrating and our calculus work and talk about the approximation of the area under a curve. What does that mean? Well, we know how to find area if it's a nice clean figure. So we know how to find the area of a rectangle, square, circles, trapezoids, those kinds of figures. What happens if the area or a region is not a nice perfect figure? What happens if we're given something like this, maybe, and I ask you to go from maybe A to B with the x-axis, and I create this figure in here, and I ask you to come up with the area of that. Well, at this point, we don't have a perfect way of finding that value. We don't have a nice formula. We could break this up. Maybe we could break this up into a rectangle here, and then we got these two smaller areas here. Well, maybe in here we could break another, maybe a square or a rectangle. And then over here, maybe into a rectangle or a square again. And then maybe here, oh, that kind of looks like a triangle, possibly. And then we could approximate using those figures, because we know the area of a square, we know the area of a triangle, rectangle, those sorts of things. What we're going to do today is we're going to approximate these areas, and we're going to use 4 different methods. And those methods are going to be the inscribed, circumscribed, the midpoint, and the trapezoid. So in example 1, we're going to give you the function x squared plus 2. We're going to go between 1 and 5, so that's our a value and our b value. We'll go ahead and label those. And we're going to cut it into 4 sections. That's important to know how many sections we're cutting it into, because we can cut this into an infinite number of sections. And when we get into the calculus portion of it, we're going to see that we are actually going to take and cut it into an infinite number of sections. But today we're just going to cut it into a certain number of sections. So the first thing I'm going to do is graph out this function, x squared plus 2. I know that I'm going to cross the y-axis at 2. I know it's parabolic, x squared. So there we go. I know that we're going between 1 and 5. So this is the region that I'm looking at. This region in here. So again, we could cut this into some rectangles, some squares, whatnot. What I want to do is to focus on these 4 methods up here. So the first method we're going to do, we should also cut that into 4 sections. So if I cut it into 4 sections, these are going to be equal sections. So I know if I cut this into 4 equal sections that these values here are going to be nice clean numbers. I go from 1 to 2, 2 to 3, 3 to 4, and 4 to 5. If I cut them at those nice integer values, then I know that they're going to be equidistant apart. I could cut this into 8 regions. If I wanted to cut this into 8 regions, I go from 1 to 1.5, to 2, to 2.5, to 3, to 3.5, to 4, to 4.5, to 5. And that would give me 8 regions. So let's go ahead and look at that inscribed method. And I'm only looking at between 1 and 5. So what I'm going to do with my graph here is kind of elongate it, so it kind of gives us a better idea of what's going to happen. So there's my 1, and here's my 5. I'm going to cut it into 4 regions. So there's my 2, my 3, my 4, and my 5. And what we're going to do is we're going to create rectangles in each of these regions. So I'm going to go ahead and draw my bars. And inscribed means inside. Kind of the way it sounds. Inside, inscribed. So I'm going to create rectangles on the inside of this figure. So I know then that this rectangle here, we'll call it rectangle A, is going to be 1 unit wide. Well, how tall is it? Well, I know this function is x squared plus 2. And at 1, that is where the height is going to occur. So I'm looking for the value of this function when x equals 1. So I'm going to find f of 1, which is 1 squared plus 2, or 3. So that gives us a height here of this rectangle A. So rectangle A is going to be 1 here, and it's going to be 3 tall. So the area of rectangle A is going to be 3. So we'll come off to the side here and say A equals 3. We're going to do the same thing for the next region. We'll call it B. Here, again, my height or my width here is still 1 from 2 to 3, still 1 wide. Now how tall is it? Well, now if I plug 2 into the function, if I find f of 2, that gives me 2 squared plus 2. 2 squared is 4 plus 2 gives me 6. So now my height is 6. So now B dimensions are 1 by 6, or 6 units. So I come off to the side, and I got now B equals 6. So now I got area A and I got area B. I'm going to do the same thing for area C. Again, I'm 1 unit wide. How high am I? I'm going to plug 3 into my function, find f of 3. F of 3 gives me 3 squared plus 2, which is 11. So C is going to be 1 by 11, or 11 units. And between 4 and 5, we'll call that section D. So section D is, again, 1 unit wide. And how high is it? Well, if I plug 4 and I get 4 squared plus 2, 4 squared is 16, plus 2 gives me 18. So this is going to be 1 by 18 units, or 18 total units. Now if I add those together, I have 11, here's 20, so I have 38 units. And that's an approximation. Now, what kind of approximation is it? Well, we can say this is an under approximation because we know that we're missing some areas. We're missing these small triangles in there, or triangle looking figures. It's actually a curve, so it's not exactly a triangle, but it looks pretty close to a triangle. And that gives us a close approximation of this. And that's our inscribed method. So I want you to see is that inscribed method is going to give us an underestimate of what the actual area is, because we know we're missing some of that area. The next method I want to look at is that circumscribed method. And if we think about circumscribed, you should think circumference. Circumference means outside. So this is going to be our outside kind of method. So I want to look at that same graph, the same figure, or the same function, f of x equals x squared plus 2. And again, I'm going to go on the interval from 1 to 5, and I'm going to do in 4 sections. So again, if we come up here, here's our 1, here's our 5, cutting into 4 sections. I'm still cutting it 2, 3, 4 to give me 4 equal sections in there. I'm still going to create these regions inside. But now, instead of creating a rectangle on the inside, or using the smaller height, I'm going to use the outside. So if I look between 1 and 2, the highest value here is going to occur at 2. So I'm going to draw a rectangle using that highest region in, or highest value in that region. Between 2 and 3, it's going to occur at 3. So I'm going to create a rectangle there. Between 3 and 4, it's going to be here. And then 4 and 5, it's going to be in there. So again, we have 4 regions. We'll call them A, B, C, and D. Again, we know the bottom width here is going to be 1 on each of these rectangles because we made nice clean sections, 4 sections between 1 and 5. But now if I look at the height of this doesn't occur at 1 like it did on the inscribed method. The height of this is occurring over here at 2. So I'm going to find the value of this function at 2. Again, I can go ahead and find f of 2 is going to be equal to 2 squared plus 2, which gives me 6. So I know that region A is going to be 1 by 6 units high, or a total of 6. I'm going to do the same thing for B. And B, again, is going to be 1 unit wide. How high is it? Well, again, the height of it is occurring at 3 this time, not at 2, but at 3. So 3 squared is 9 plus 2 gives us 11. So we have 1 by 11 or 11 units. We're going to do the same thing for region C. Region C, our highest value is occurring here at 4, creating that rectangle. 4 squared gives me 16 plus 2 gives me 18. So I have a 1 by 18, which gives me 18 units. And then unit or section D, if I come up here, my highest value is going to be at 25, or at 5. So 5 squared gives me 25 plus 2 gives me 27. So it's a 1 by 27 units. Now I can go ahead and add those up. I get what? 20, 30, 45, 55, 56, 62 units. Again, this is in square units. We're talking about area. So what do we know about that? Well, we know that this is an overestimate. So our inscribe method gave us 38, remember? That was an underestimate. And we know the overestimate is 62. So we know the area of this region is somewhere between 38 and 62. Well, can we do a better job of approximating that actual area? And the next two methods are going to get us pretty close to what we want. And the next method I want to talk about is the midpoint. Midpoint gets to be a little more cumbersome, hairy if you wish. So the midpoint, again, we're going to look at the same function. F of x is x squared plus 2. We're going to go from 1 to 5. And again, we're going to still keep it in 4 sections. And again, I'm going to elongate this pretty much so we can kind of see what's happening. So we're going to go from here 1, here's the 5. We're going to cut this into 4 regions again. So we're cutting it 2, 3, and 4. So now what we're going to do is instead of taking the lower end or the upper end, we're going to take the midpoint. So the midpoint between 1 and 2 gives us 1.5. Between 2 and 3 gives us 2.5. 3 and 4, 3.5. 4 and 5 gives us 4.5. And what we're going to do is we're going to take this value and go up to our curve and then create our rectangle. And what I want you to hopefully notice is that as we create these rectangles, we see that we have a little bit on the outside and a little bit on the inside. Again, a little out on the outside, a little on the in, out, in. And hopefully we see that there's almost the same amount of area on the outside as there is on the inside. Not exact. Again, this is just an approximation, but we're getting close to that value. So how do I find the area of these? Well, again, each of these regions is still 1 unit wide. So we're still going from 1 to 2, 2 to 3, 3 to 4, 4 to 5. So 1 unit in there. But now for the height, we're looking at 1.5, 2.5, 3.5, and 4.5. So you're probably going to want your calculator. So we're going to take 1.5 and we're going to square it. And then we're going to add 2 to it. So we're going to look at f of 1.5, which gives us 1.5 squared plus 2, which gives us 4.25. So again, we can call this region A if you wish. And we'll come off to the side here. A is 4.25 by 1. By 1 or 4.25. For region B, here we're taking 2.5. So we're going to take 2.5 squared, and we're going to add 2 to it. And that's going to give us an 8.25 height. So the height of this is 8.25. We're still 1 wide. So to find the area, we have 8.25 times 1, which is 8.25. For region C, we're taking 3.5. We're going to square it and add 2 to it. And that's going to give us 14.25. Again, we're still 1 wide. So we have 14.25 by 1 or 14.25. And finally, region D, we take 4.5 and square it and then add 2 to it. And that gets us 22.5, or 22.25, sorry. So we have 22.25 by 1 or 22.25. So if we did our math correct, this should be somewhere between 38, which was our underestimate, our inscribed, and 62, which is our circumscribed. So what we got? We got 22 and 14 gives us 36. And here is 12, so we have 48. Plus 1 gives us an area of 49 square units. And that is definitely between 38 and 62. Again, not exact, just an approximation. We'll eventually be able to find the exact. And finally, what I'll look at is that trapezoid method. So we're going to look again, same function, f of x equals x squared plus 2. We're going to go 1 to 5, and our n is going to be 4 units, or 4 sections. So again, I'm going to exaggerate this just a little bit. We're going to go from 1 to 5. We're going to cut it into those 4 units, or 4 sections. But now what we're going to do is we're going to create trapezoids in here. Remember, a trapezoid has 2 parallel sides. So those parallel sides, the other sides, they can be angled or they can be perpendicular there. So that can be a perpendicular line, maybe an angled one there. So here, if we create those trapezoids, we should see that it follows that curve pretty doggone close. So if I create my 4 sections, A, B, C, and D, how do I find the area of that trapezoid? Remember, the area of a trapezoid is 1/2 of the 2 bases added together times the height. Well, how does that play in to this trapezoid here? Well, if I take this figure here and kind of make it into a figure that looks like this, or turn it on its side, there would be my A. So my 2 bases here are going to be actually the heights up to this function. Well, I know the value of this is 3 at 1. The value at 2 is 6. So I know I have a 3 and a 6 for my 2 bases. My height of this trapezoid is actually the width of this region. And the width of this region is still 1 unit. So the area of A is 1/2 of base 1 and base 2. So 3 plus 6 gives us 9 times the height of 1, or 9/2. For area B, we have 1/2. Again, the 2 bases are the 2 side lengths. So I already have 6. If I plug 3 in, I get 11. So I get 1/2 of 6 plus 11 times the height of 1, or 1/2 of 17 times 1, or 17/2. Region C, 1/2. My 2 bases are going to be the 2 heights again, or 11 and now 18 added together times 1. So that gives me 29, so 1/2 of 29 times 1, or 29/2. And finally, region D, I have 18, I have 27, so I have 1/2 of 18 plus 27 times 1. That gives me what? 20, 30, 45, so 1/2 of 45 times 1, or 45/2. Again, I pull out the calculator there. I'll take my 45 and my 29, my 17, and my 9. That ends up giving me 100/2, or 50. Again, that's pretty close to what we had for the midpoint. Remember, the midpoint there, we had 49 units. And again, 50 is between that overestimate and that underestimate of 38 and 62. Now the question always becomes, how do we get to a better estimation? And real quick, without giving you too much more to think about today, is if we were to take this region from 1 to 5, and instead of cutting it into 4 regions, we cut it into 8 regions. So we got 1, 2, 3, 4, 5, 6, 7, 8 regions in there. So now we could do all of those methods again, but now instead of being 1 unit wide, they'd be a half a unit wide for each one. And we go up to the heights on our graph. Well, what can we do even more? We could cut this into 16 regions. So we cut each of those in half again. And what we could do is we could continue to cut these into half in a smaller and smaller section as we take this n value, we call n the number of sections, going to infinity. And eventually we're going to take the limit, remember our old friend limit, as n goes to infinity of these regions. And that's going to give us the exact area of this figure coming up shortly.